Hello, welcome to this video presentation for ICS V27. My paper title is Array of Piezoelectric Energy Harvesters for Broadband Natural Frequency Applications. My name is Salam Khuritum. I am Assistant Professor, Mechanical Department, Faculty of Engineering, Alexandria University. This video presentation contains four main parts. The first, introduction. The second, modeling and simulation. The third, results and discussion. Frequency response and stress analysis of the harvesters. The fourth, conclusion. Introduction and literature review. Aim of study, conversion of mechanical energy to electrical energy using piezoelectric material. Maximizing the harvester efficiency using an array of harvesters, 3 cantilevers, to broaden the operating natural frequency. Studying the effect of two materials of piezoelectric, PCT5A and PVD-F, on the output power and factor of safety. Piezoelectric, PCT, energy harvester. The harvester consists of a cantilever of steel is attached with PZT layer with high power per unit volume and a tip mass. The harvester parameters are the thickness of piezoelectric and steel materials, the width of cantilever, the total length. The harvester is subjected to a base excitation that produces bending stress on layers, then generate voltage. Electricity generation, bending stress, modify and changes BZT dimension, then changes the bond length, then generates voltage on surface of BZT. Broadband natural frequency technique. The proposed technique depends on 3 graded different thicknesses cantilevers with 6 masses that display 6 peaks of the first and second mode. 2 peaks of the first beam and thus 2 peaks of the second beam and 2 peaks of the third beam. This is the first mode frequency response, the second mode frequency response. Generated power of the harvester operates the sensor nodes. Generated power used to perform predictive maintenance operations, to design self-powered devices to save time and money for replacing the batteries. Range of power and its application. Figure show the range of power and its application, energy harvesting application. The first column of the figure shows the excitation of car, human motion, building. The harvester, this harvester generates power from excitations to operate sensors. These sensors can be used in tire condition monitoring or pacemaker or condition monitoring, as shown in this figure. Modeling and simulation. We utilize the finite element using COMSOL multiphysics to model the proposed design. The utilized equation of power is function in some parameters: voltage, electromechanical coupling, the natural frequency, the resistance load, the capacitance, the piezoelectric constant. Proposed design model consists of 3 gradient different thickness cantilevers, and each cantilever consists of base material of steel, a piezoelectric batch of PZT5A or PVD-F, a tip mass, and arranged masses to wind the natural frequency. Function of arranged masses is to control the frequency range, give high power for the second mode. The properties and geometric parameters of the base material and piezoelectric materials. Table 1 shows the properties of the base and the piezoelectric material. Table 2 shows geometric parameters of the piezoelectric array harvester. The total length of cantilever is 120 millimeter. The total length of the piezoelectric is 15 millimeter. The width 20. The thickness of the first beam is 0.4 and second beam is 0.55. The third beam is 0.7 millimeter. The weight of each mass of the 6 masses equals 10 grams. The harvester is subjected to base excitation Z equals 2 millimeter in that direction. Natural frequency study. Figure shows the bending mode shapes of the first mode and second mode. The natural frequencies of the first bending mode of cantilevers were 11 for first beam, 13 for second beam, 20 for third beam. The natural frequencies of the second bending mode of the three cantilever were 74 for first beam, 105 for second beam, 189 for third beam. Results and discussion. The methodology. The proposed model is simulated using finite element COMSOL to study the effect of the tip and arranged masses. The conducted studies. Eigenfrequency study to determine the natural frequencies and mode shapes. Load resistance study to determine the optimal resistance. Frequency response study to determine the response of the voltage and the power in the frequency range from 5 to 230 Hertz. Load resistance optimization. Load resistance response is a relation between resistance on the x-axis and power in y-axis. This figure shows the load resistance dependence of the first and third beam. The optimal resistance is the point of maximum outpower in this point and this point. The optimal load resistance was found to be 500,000 ohm. Frequency response for the power and voltage of PZT-5A patches. Frequency response is a relation between frequency on x-axis and power on the y-axis. Table shows the maximum power versus the power. The power of the first peak is 0.92. Of the second peak is 2 milliwatt. Of the third peak is 5.9. For second mode, the first peak is 24. For second peak is 31. For third peak, the third peak is 87. Acceleration equals omega n squared z. From this relation, as the frequency increases, the acceleration and the stress increases, thus the output power. Frequency response of the power and the voltage of 4 BVD-F patches. The low coupling coefficient of PVD lowers the output power. The stress analysis of the harvesters. The aim, studying the stress to avoid the failure. The base excitation and inertia forces generate the bending stress. To avoid failure, stresses must be less than the endurance limit of the material. Factor of safety for the PZT-5A and BVD-F array harvesters. The life harvester depends on the frequency, load type, and temperature condition. Factor of safety equals SE, endurance limit, or the strength of material, divided by the stress. The minimum factor of safety for PZT-5A is 2, and for BVD-F is 7.6. The stress distribution of the array with PZT-5A figure shows the stress of the second mode is higher than the stresses of the first mode. Conclusions. The proposed design displays an improved wideband natural frequency from 7 to 230 Hertz. The output power of the second mode is 14.7 of the output power of the first mode, 5.9 milliwatt. In the case of PZT-5A, the output power of the array of PZT-5A, 71.3 of the output power of the array of BVD-F, 1.22 milliwatt. The stress analysis for the two materials is conducted to avoid failure. The results recommended the PZT-5A in the harvesters with low excitations and BVD-F in the harvesters with high excitation. Thank you. Questions? I will happy to answer your questions.